How do we take a messy, complex curve and perfectly reconstruct it using simple algebra? The answer lies in infinite polynomials. When you type standard exponential or trigonometric functions into a computer, it evaluates an infinitely long polynomial to arrive at the correct value. This page from Rudin's text shows the formal definition of these structures, known as power series. Look at definition 3.38. The sequence Cn provides the fixed coefficients, the structural DNA of the series, while z remains the variable complex input. This formula defines a function of z, where the specific behavior of those discrete coefficients determines exactly how far the series can reach into the complex plane. In theorem 3.39, the root test requires the nth root of terms to drop below 1, defining alpha as the limit supremum of the coefficient's roots. In the proof, isolating z forces the radius of convergence, r, to equal 1 over alpha. Now let's take a look at the two mathematical extremes. In example 3.40a, the coefficients include n to the n. This fast growth pushes alpha to infinity, forcing the radius of convergence to 0. Conversely, in example b, the factorial denominator shrinks terms so rapidly that alpha collapses to 0, expanding the radius r to infinity. Geometrically, this means our first function can only exist as a single, isolated point at the origin. Our second function, however, thrives everywhere, seamlessly covering the entire complex plane. The radius of convergence acts as an absolute mathematical border. Inside the radius, the function holds together. Step outside that boundary, and the sum shatters into infinity. But what happens exactly on that borderline? Example 3.40c shows a baseline geometric series with a radius of 1. Plugging in an absolute value of 1 for z, the terms fail to trend toward 0, meaning the series diverges. Think of this visually. The green interior is safe. The red exterior breaks down, but that dashed yellow boundary line is highly unstable. Look at example D. Here, the terms are divided by n. The overall radius of convergence is still 1, but the behavior on the boundary line changes depending on your exact coordinates. If c equals 1, we get the harmonic series, which diverges. However, because the coefficients decrease monotonically to 0, Theorem 3.44 proves that the alternating sign logic of the complex variables allows the series to converge at every other point on this ring. Now it's your turn. Pause the video and look at example E. If you set the absolute value of z to 1, what happens? Try applying the comparison test yourself to solve it. Because the absolute value simplifies to 1 over n squared, and 1 over n squared is a convergent p-series, it converges absolutely at every single coordinate. Our boundary forms a solid green ring. Because standard root and ratio tests yield a value of 1 on this edge, they provide no information. The boundary will always be a wild west that requires manual, individual testing. Let's consolidate these rules. First, power series act as infinite polynomials, mapping coefficients to functions. Second, convergence is dictated by distance from the center, calculated via root or ratio tests. Finally, the boundary is unpredictable and needs manual evaluation. This transition from discrete sequences to analytic functions is the foundation for performing differentiation and integration on infinite sums. If this breakdown helped clarify the mechanics of power series, subscribe and follow along for more structured deep dives into classic mathematical texts.